Alright, so we're going to finish Unit 2, Lesson 6 today, and take some notes, and then I want you to go ahead and try worksheet number 5 in small groups after this. So, yesterday, we derived the kinetic energy equation as EK equals 1/2 mv squared, where EK is your kinetic energy, and joules, M is your mass, in kilograms, and V is your velocity in meters per second. So we can put that one up here on the board over here. Alright, the next one we're going to derive is gravitational potential energy. And so in this one, we're going to just look at an object like this. Okay, what kind of force does it take to go from one level to another level? Right? If we were to graph that, it would look like this, where this would be like position 1. You can see on the graph, that would be like position 1 there. Here would be position 2. Okay, so it's the same amount of force to go from 1 to number 2. Okay, so if we were going to graph our force versus height, like it shows up there on the screen. Let me get this here. So if we were to, again, like I said, graph our force versus our height, it would look like this. Alright, so now the question is, what does this area here represent? And it's a force in newtons and a meters over, height is in meters over here. So if we were to multiply those out, you'd end up with a newton meter for your area here. So if we were going to calculate this area like we did in the last time, this area right here would be base times height. Last time we did this, it was a 1/2 base times height, but if we were going to do here, so it would be force times our height. So that's essentially our gravitational potential energy is if we take our force due to gravity times our height, you get our essentially your gravitational potential energy. So this equation looks like this. Eg is equal to force due to gravity times height. Force due to gravity is equal to mass times 9.81 newtons per kilogram, like so. So we can substitute that in here. So Eg is equal to m times 9.81 times h, which is your height. So this is mass, kilograms, h, which is height, in meters. Okay, again, so the higher you are, the bigger that number is going to be there. This number here is what's called the gravitational field constant, and that changes based on where your location is altitude-wise from the center of your planet. It also changes based on your large astronomical body in which you reside. Okay, so now how we get working, which is our last equation we're going to derive. First, let me put that up there. M times 9.81 times our height. Okay, so how we get working is it's defined as the transfer of energy by an external agent applying in the force parallel to the direction of motion. For example, if my system's this mass, to add energy, I exert a force upward and it causes that to change. Now, to calculate that, the work, it is actually force. It has to be parallel to the motion that you're traveling. So work is equal to force times the ever amount that you move in whatever direction that you're going. So let me get that out here on the board. So work equal to force parallel times your delta x, which is your displacement or how far you go or how far you move. So that's work. The unit for that is Newton meter, which simplifies to a joule. Force is newtons, and then delta x is distance or displacement. And the unit for that is meters. Okay, so we're going to go F times D delta x. We'll just call it like this. Let's actually change this to D right here. That'll make it easier. Force times our distance there, like so. And that has to be parallel. So then we'll work that out, what that parallel part means in some of the problems. So when you put this all together, work is what causes all the change in energy. So work, as you can see down here, work causes our change in energy. If you pick an external change and you cause a distance change, you'll cause that a change in any of those energies. Okay? That's the first law of thermodynamics. Alright. So let's go ahead and try this and apply this to example problems. Alright, so I'm going to do 2 example problems and I'm going to model the best way to do it for you, and then using our LOL graphs. And so worksheet 5 then is a bunch of LOL graph type problems. So again, I want you to try them. The biggest thing is to try them. Okay? And then on Monday when we get back together, or the next day that we get back together in class, we'll go over it and make sure that you understand. And then we'll have another follow-up worksheet to it. Because we have a lot of different things that could go on here. So in this first situation, we have a snowboarder that starts from rest at 5 meters and 5 meters above the ground on a frictionless track. Oops. So I'm going to just highlight our different terms. So we got 50 meters there above the ground on a frictionless track, flies off the track at a 45-degree angle above the horizontal at a height of 10 meters. Okay, disregard air resistance. So it says, what's the skier's speed when leaving the track? And then, what's the maximum height attained? And we're going to use energy, our principles of conservation of energy, to solve all these problems. So, there's actually 2 parts to this problem. There's part 1, what's the skier speed when leaving the track? And then the maximum height after they leave the track. Okay, so we'll do that first part. So we'll start with our LOL graph. Okay, so we're going to look at the initially, and then E, end of track, or whatever, the ski jump or whatever it is. So I imagine that it looks something like this. So you got a snowboarder. There they go. You're going to go down the track and fly up. So we're looking right there at the end of the track. And that's at 45 degrees above the horizon there. So let's talk about, first of all, what energies. Again, I'm not actually going through that problem yet. I'm going to first do the energies. And it might seem a little weird, but again, it'll help us in the long run. So at the beginning, all they have is EG right there. And I'll calculate the amount of that in just a moment. At the end of the track, okay, if the skier is my system, or the snowboarder is my system, this guy will have EG because it's a little bit up high, and he'll also have EK. And then proportionality we don't know yet. He'll have less EG and more EK. We'll see that play, but we'll get the numbers out in a second. Okay, so the thing is it's actually asking about the skier's speed. Right there. So the trouble is where is the velocity buried in? Well, the velocity is buried in this EK right here. So if we can find that EK, then we can find the velocity, hypothetically. Okay, so let's go ahead and try this out. So he's up here, he's 50 meters. That's a really high jump. And then up here he's at 10 meters when he leaves the track. Right there. So here's how the conservation of energy works. Since there's no work in or out, there's no friction, the EG over here on this side, on the internal side, the EG equals, on this side, the EG plus the EK. So if we can somehow find, again, get to this EK, we might be able to solve the problem. So let's go ahead and put our equations in for each of these. So that's M times 9.81. Let me start over. Just scoot back just a little bit. M times 9.81 newtons per kilogram times our height equals, we'll call that height 1, M times 9.81 times newtons per kilograms times our height 2 plus 1/2 mv squared. Again, we're trying to find that speed right here. Now the problem is, if you look at this, we can plug in our next set of numbers. So M times 9.81 times my height, which is 50, equals M times 9.81 times 10 equals that 1/2 mv squared. The problem is I don't have mass here. Okay, so I have two unknowns and that's it. So that's a hard problem to solve. So if you're clever about this, if you can see, there's a little math trick you can see here. The question is, what can you divide out of this equation? Alright, what can you divide out? Well, this has an M, that's factored out. That has an M, that's factored out, and that has an M. So you can actually factor out an M out of my equations here. So what we end up with is 9.81 times 50. Let me get my calculator here. So that's 490.5. So that would be newtons. That's a meter. And this was newtons per meter, so we're at newtons there. That's, yeah. Alright, so 490 equals 98.1 plus 1/2 v squared. So now all we have to do is solve for our v squared here, right there. So subtract 98 from both sides. Alright, so that's 392.4.